Here is a summary of some of the things we learned about prime ideals and maximal ideals. So R is a commutative ring with 1. A proper ideal M in R is called a maximal ideal if there is no proper ideal in R that properly contains M. So you have M and you have R. If you have something in the middle, another ideal, then this guy has to be either M or R. That's what it means. And we had this lemma, how to recognize a maximal ideal. A proper ideal is maximal if and only if, when you quotient by it, you get a field. Then we had a definition of a prime ideal. A proper ideal P in R is called a prime ideal if whenever product of two elements A and B is in P, then one of those elements has to belong to P for all elements A, B in the ring R. And an element of the ring is called a prime element, a non-zero element, if the corresponding ideal that it generates is a prime ideal. We had a recognition principle for prime ideals also. A proper ideal is prime if and only if when you quotient by it, you get an integral domain. And then we have, I want to recall two little things that we learned about prime ideals, primes in general, in principal ideal domains. Remember, principal ideal domain means an integral domain in which every ideal is principal, means every ideal in this ring has to have the form for some x generated by a single element. So here's the first lemma. Non-zero prime ideals in a pre-ID are maximal. Remember, maximal ideals are always prime, but in general, prime ideals need not be maximal. There are more prime ideals than maximal ideals, but in a PID, any non-zero prime ideal is automatically maximal. That's one thing we proved. And the other thing we proved is this fact about identification of irreducible elements and prime elements. So in any integral domain, prime elements are always irreducible. Irreducible means that it has no non-trivial factorization, recall. And non-zero, non-unit element is called irreducible. A is irreducible if whenever you write A as a product U times V, one of these guys have to be a unit. So there is no way to non-trivially factorize A. So prime elements are necessarily reducible. And if you are in a PID, then the reducible elements are also prime. So in a PID, the prime elements and the reducible elements are the same. Okay. So I want to recall all this because we'll need all this in this result, which is sort of a jumping off point for field theory, which will only indicate just a little bit. Well, this is basically the content of most of chapter 5, but now we have it basically for free because we have proved all these results on the left. So this is about studying quotients of fx, where f is a field. So the first thing I want you to recall is that fx is a PID. This we have proved. Recall. F is a PID. I mean fx, I'm sorry. F is a field. What am I saying? Recall fx is a PID. And this follows from division with remainders, right? So you take, given any ideal, you take a smallest degree non-zero polynomial in this ideal and show that the ideal consists of all multiples of this polynomial. So every ideal in fx has the form parenthesis fx for some polynomial fx in capital Fx. It's generated by a single polynomial, meaning it's all multiples of a single polynomial. Okay. The theorem describes the nature of the quotient fx mod this ideal when f is a reducible polynomial. So let f be a non-zero polynomial in capital Fx, then the following are equivalent. And I'll write 5 statements. One, that f is a reducible polynomial. Two, that the ideal that it generates, by the way, we are sometimes writing f, sometimes writing fx. It means the same thing, it's just a matter of convenience, is a prime ideal. Three, when you quotient by it, you get a domain, integral domain. 4, f is actually a maximal ideal. And 5, fx mod f is a field. So if you look in the book, they have to work a lot to get this theorem in chapter 5 because they don't have the general language of quotient construction and the general theorems that we have. But for us, we basically know all these equivalences. And I have pretty much recalled everything on the left. So let's go through this. The equivalence of 1 and 2 follows from this lemma, because irreducible polynomials are nothing but irreducible elements of the ring Fx, and irreducible elements are the same as the prime elements because Fx is a PID. Follows from the lemma down here. Let's give these lemmas names. Call this one 1. This is just temporary names, but for this discussion, 1, 2, 3, 4. From 4, lemma 4, since this is a PID and irreducible polynomials are just the irreducible elements of Fx. If you look at the definition of irreducible polynomial, it's really exactly the same definition as the definition of the irreducible element. Okay. 2, if and only if 3 follows from this recognition of prime ideals, right? Where is it? 2. Lemma 2. Okay. 2, if and only if 4 follows from lemma 3, I suppose, since Fx is a PID again. So in a PID, non-zero primes are maximal. F is a non-zero polynomial. If this is a prime ideal, then it's a non-zero prime ideal, so it will be maximal, and maximal ideals are always prime. So that's 2 if and only if 4. And 4 if and only if 5 follows from the recognition of maximal ideals from lemma 1. Yeah, so the results that we have proved so far exactly give us this. So the upshot of this is that, so in particular, the theorem says if f is a irreducible polynomial, then when you take the polynomial ring and quotient out by the ideal generated by this irreducible polynomial, this is a field. And in fact, we will see that we can identify f inside this field. Let's call this field K in a natural way. So f, of course, sits inside f of x as degree 0 polynomials. And then from here, you have the quotient map to the quotient. And if you just take the composition, this gives you a map from f to this k, and this is the injection. It's a one-to-one map. It really takes us constant and sends it to the corresponding coset. Yeah, and you can identify f inside k using this map. This map. R goes to the coset of R. So K is a field containing F. And this gives us rather interesting construction of fields. For example, if you take real polynomials, x squared plus 1 is a reducible polynomial in Rx because x squared plus 1 is always strictly positive, so it has no root in real numbers. When you quotient by it, we will see that this is really just complex numbers. If you take the image of x in here, the coset of x, and call it alpha, then alpha squared plus 1 is x squared plus 1 plus bracket x squared plus 1, meaning the coset of x squared plus 1, but that's the 0 of k. So alpha is an element in k such that its square is minus 1. And you can check that k is really just all elements of the form a plus b alpha, where a and b are real numbers. So k is an abstract algebraic definition of complex numbers. In fact, we can show that k is isomorphic to your usual complex numbers. So this alpha is a formal version of what you call I, square root of minus 1. What we have done is we have taken the polynomial ring and we have quotiented out by this polynomial, meaning we have forced this polynomial to be 0. So we have forced x squared to be minus 1. So if you take the image of x in this quotient, which is our alpha, the square of that is literally minus 1. By minus 1, I mean minus 1 of k. Okay. So this gives us a way to formally add solutions of polynomial equations and then study solutions of polynomial equations this way. Because you know now that in this field, the fundamental theorem of algebra says that all real polynomials can now be solved in this field. So this is extremely important for study of solutions of polynomial equations. We'll study this example, fx mod an ideal, in some more detail.